So now I'm going to explain how the accelerometer works. So once we have set the GPL pins and initiated it, we have set a 3-second delay before we read and assign the first ever X and Y values we get. Just the first, so we can calibrate the car to calculate the height. Reason why we set a 3-second delay is to ensure that when we plug in the wire or do anything to the car, it won't affect the initial reading of the values. So why we want to calibrate the car is because let's say if the ground is slanted on the side that where we are testing our car, the height might be inaccurate as we are calculating the height via tilt or gradient. Once we have read the first values, we run a loop in the main to constantly get the X and Y difference between the current X and Y values compared to the first X and Y values. We then proceed to get the average difference between the X and Y values. So we calculate height by dividing the difference, which is a constant that we calculated. So how did we get the constant? Was basically using the formula of y1 minus y2 over x1 minus x2. I compare the X and Y average values with a actual 5 cm and 2.5 cm height. Then I divide the values accordingly to get the values when the car is at 1 cm. So basically we calculate by gradient. In layman terms, it is by tilt. Before all this, I only used the X values, which proves to be quite noisy as it only uses one-dimensional data. I then implemented a better idea, as said previously, using both X and Y to get more data, resulting in a cleaner value. In order to use both X and Y values, I have to position the accelerometer in a slanted way on the car. Now I'll be talking about the kind of filters that we implemented. So the first filter was to remove all height that returned to be negative. As we know, tilt goes into both ways, so if it tilts the other direction, it will result in negative values. And this is all happening due to the noise when the car is moving. So basically, any values below 0, we set it to 0. The next filter, we applied it to only start detecting hump when the height is equal or above 0.7 cm. Not only that, we actually started to count the average only when the height is above 0.7 cm. This is to ensure that the noise generated when the car is moving does not affect the height that we want to calculate. So anything below 0.7 cm will be taken as not a hump and thus not added into the calculation of the average height for the hump. How we have done it is to implement a count, and it will start counting every time it loops through the function when the height is above 0.7 cm. We will then add up all the height calculated and divide it by the count. This way, we can get the average height when the car is actually above 0.7 cm or when the car is actually moving through the hump. So we can get the average height. The next filter we did is actually an extension to this current filter to detect a hump. So previously, we said that we only think it is a hump if the height is above 0.7 cm. But due to noises, sometimes the height gets above 0.7 cm when the car is moving, thus rendering the height detection function useless. Due to this problem, we improved the filter by adding another filter within the previous filter by only detecting if the car is going through a hump if the height is above 0.7 cm for more than 15 counts. The 15 counts act as a confidence level. We got the value 15 from vigorous testing as we are pretty confident that if the height stays for more than 15 counts above 0.7 cm, it is definitely a hump. After all this, we set the height and count all back to 0 so it resets and ready to calculate the height for the next hump. Here are the results of the filter for the accelerometer as shown in the graph. As seen clearly, the blue line has lots of noise as compared to the green line, which has 3 filters applied to it. I would say that our filters work hand in hand to actually ensure that our output is clean and accurate. For the ultrasonic sensors, we kind of use the same way to get the distance, which is to find a constant and then calculating it to the actual distance to get the accurate distance. However, due to different ultrasonic sensors being built differently, we have actually added a offset feature to add or minus offsets to make the distance for the ultrasonic sensor accurate. The filters we applied to this was to get the average distance by calculating the latest 50 values and dividing it by 50. This way, our values will be cleaner as there are some spikes here and there. The next filter we applied was to remove any negative values. Those negative values comes from the offset that we have set, as some of them are negative. Here are the results of the ultrasonic shown in the graph. Without the average filter, as seen at the end of the graph where the car is moving, it is very noisy. As you can see, there are also no negative values thanks to the filter removing all the negative values. As you can see, our codes for the accelerometer and the ultrasonic sensor are fully integrated and can work hand in hand together, outputting data to the serial monitor at the same time. Here is our main function calling both functions in the ultrasonic and the accelerometer. Here is our black and white box testing. Our state diagram.